Hi, my name is Mark Sagar, and I'm joined in this presentation by Alistair Knott and Martin Takach. And we will be talking about a platform for embodied modeling of infant cognition. In this particular paper, we'll be talking about the event perception component of it. We're taking a very holistic approach to modeling infant development. We're building a computational model, a cognitive architecture of infant development, but also combining that with experiment working with developmental psychologists. And we want to look at how all the different components that come into human behavior, especially involving early learning, come into play. Baby X is a virtual infant, and it's a simulation where we have created both a computational simulation of the behavior and physiology, but also a computer graphics representation so that Baby X appears real, so that you can interact with her in real time. So this means that we've had to build sensory systems, including even interoceptive systems. We've had to build models of visual attention, object classification, reaching, object tracking, all kinds of things, also including an emotional system, because that's such a key part of behavior. And we even have virtual neurochemicals in the system to help modulate those behaviors. Now, for Baby X's memory, we've created models of working memory, including long-term episodic memory and emotional memory. And all of these are fitting into a context which supports modeling of language. Now, how do we evaluate such a model? Well, in a way, we're doing a Turing test of early behavior. So we want to compare Baby X's behaviors with those of real babies. And if we can create an experiment in which a caregiver interacts with Baby X in the same way that a caregiver would interact with a real child, and we get the same type of measurements out of it and the same behaviors, then we are achieving a Turing test of early behavior. In order to do this, we've created a shared interaction space where real parents or caregivers interact with real infants across a touch screen, and they do various tasks associated with cognitive development, such as social games or language learning tasks or so forth. So in the picture, you'll see a mother and a child on two different sides of a virtual screen. Now, when we replace the real child with Baby X, we then record how the mother interacts with Baby X, and we get Baby X to try to elicit the same type of behaviors, but Baby X also has to do the same type of learning.
Here's a wee demo of a real baby interacting with a real parent.
I'm moving the horsey.
See, she's talking about the action she's doing. The baby is experiencing events.
Are you moving the piggy?
She's also executing events by moving objects herself.
Now move the doggy and the ducky.
Everyone's talking about these things.
What about the sheep, Andy? Where's the sheep?
So as you can see, she's looking for the sheep, and I'll just sort of scrub through.
Good girl.
And she finds the sheep.
Yes. Yeah.
Here's an example of Baby X in exactly the same environment. Did you hear the user, it's marked here, ask, where is the baby? Oh, sorry, where is the doggy? And so the baby is looking around. You can see where the cursor is here. This is where her eye is looking. She finds the dog and moves it. So that's a movement action we saw.
I'm going to move this one.
But here's the mark in loco parentis doing something else. He's moving a sheep.
Good.
A lamb. So in this talk, we are focusing on the baby's ability to represent events. So the basic idea is that an organizing principle for the whole model is that babies kind of like iterate in units of whole events. So they experience an event, then another event, and then another event. So that's the sort of high-level unit of analysis. So there's very good evidence that that happens in adults, and I'm thinking particularly of Jeff Sachs's work since 2000 or so, to now. And there's also good evidence that babies do that sort of thing, and that evidence is also quite recent. So what we're going to be talking about in the rest of this talk is the model that we're using for event processing and event representation in our baby. So here's a quick summary of that. In the outer loop, what happens is that the agent experiences an event through a sequence of relatively discrete sensory motor operations, what Dana Ballard calls a deictic routine. So some of those operations are things like attending to objects, classifying objects, or making motor movements in relation to attended objects, and so on. But some of those things get recorded in working memory in a medium that holds fields that represent information about the event that's currently underway. So for instance, that might represent the agent of the event, or the patient, or the action, or the result, or something like that. When the event is complete, then the working memory representation is used to update two long-term memory media. This is classic Jeff Sachs. One of them is a memory for events and event types, and the other one is a memory for sequences of events, which is more or less like episodic memory. And when you've experienced an event and registered it in long-term memory, then you move to the next event, clear the working memory medium, and move on. So a key thing in our particular model of event processing is that some of the operations that you perform in this deictic routine are not directly sensory motor, but are to do with setting a particular mode of connectivity for the remainder of event processing. So the idea is that you can select a particular neural circuit to continue with, and often neural circuits compete with one another, and you have to choose one of them. So you have to choose between what we call alternative cognitive modes, and for that purpose, the brain gathers accumulators of evidence for putting you into different modes. So the accumulators combine bottom-up invocation that comes from the retina or from a perception with top-down guidance that comes from long-term memory. So a quick schematic look at the mode choices that you can make. The key thing is that after you've made one mode decision, for instance, this is one branch up here where you just attend to an object. But here's another branch where you're deciding to make an action yourself. So the event here is going to have you as the agent. So the box is telling you about things that are registered in the working memory representation. So there are three choices here: attend object, or make an action, or observe some event out in the world that you're not part of. If you make an action, there are various other choices. And this is just to give you an idea that we have a sequence of mode setting operations. And basically each branch in this kind of branching tree can be thought of as a representation of a certain semantic type of information working memory. So Martin is now going to talk to you about how this tree of choices within deictic routines is implemented in our baby.
So on the left side, we see the branching tree that Ali just described, and the active branch is shown in green. So we can see that baby is looking around, she is attending to a sheep, and she has successfully classified it, and is, yeah, that's what Ali is showing with his cursor. Okay. In the second short video, we see that she's in the middle branch, which is action execution. She decided to act, and she's already attending to a sheep. And now she will reach for the location of the sheep, and she tries to move the sheep to a new location, which comes from the memory. Yeah, that's what we saw. And next, please. Here for a short moment she's attending to a dog again, so it's what we saw before. She's in attend object mode. And next slide, please. And here is what's the main point of our paper. So in this video, it's the adult that's moving the animal with her mouse, and the baby is attending to the dog, and we see in the bottom branch that the classifier has classified the dog and it's being tracked. And when the movement stops, the event is recorded, and yeah, and it ends with a little green dot, which means that it was successfully recorded. Next slide. So to quantitatively evaluate this, we compared this with some gold standard that we established from the videos recording baby-parent interactions. So we took 10 videos of baby-parent interactions, and we automatically detected all the events and then manually verified if they are correctly recorded and compared our system to that. And out of these 246 actual events, our model was able to correctly detect 100, and in 73 of these the patient or the animal was correctly established, and there were some small number of false positives. So the model mainly failed for very short events, so which we can prove by when we excluded events shorter than half a second in duration, the results got better. This is the second line in the table. So it's still not perfect, but keep in mind that we made the task very hard for us by modeling the whole baby with all the circuits running in parallel and influencing each other. So and by the way, real babies are not perfect in this task as well. So we're working on improving it, but in the meantime, this is where we got. And the main point of our paper was presenting a methodology for doing this experiment. So you can read more about it in our paper, where we also have a link to further demo videos.